Hi, everyone. My name is Guillaume Raymond. I'm an MSc student here at the University Laval. Today, I'm going to present a part of my MSc thesis, which is titled Spatial Variation of Fluid Flow Conditions for Orogenic Gold Mineralization in the Ogmito-Buzan segment in the Abitibi subprovince. So this project is under the supervision of Professor Georges Baudouin and the co-supervision of Professor Christophe Laflamme, as well as in collaboration with Benoit Canel and Christophe Schaffer. So first of all, special thanks to our industrial partner, Yorbo Resources Incorporated, as well as our academic partner, of course, University Laval, the E4M Research Chair and the NSERC Agnico Eagle Industrial Research Chair in Mineral Exploration. So first of all, as you all know, here at ULaval, our goal is to bring a better understanding of the auriferous fluid system. Our large-scale objective is to investigate the source, the timing, and the sink of the mineralization. This particular work is focused on the sink, so the mechanisms related to gold endowment, but at a deposit scale. But what controls spatial variations of gold endowment in general? We know from the literature that gold precipitation is related to changes in fluid flow conditions, and stable isotopes such as oxygen, carbon, and hydrogen are powerful tools to monitor changes in the fluid space condition. We can monitor the temperature, the fluid-rock interaction, and the different sources. So the objective of this work is to compare the variations of fluid circulation condition between the endowed and less endowed area of a deposit using these isotopes. So the study area is the Ogmito-Buzan segment in Rouyn-Noranda in the Abitibi, which is an orogenic gold occurrence that covers 12 kilometers along the Cadillac-Larder Lake Deformation Zone. It has an important potential in terms of gold-bearing content, and the choice of the study area is based on the irregular distribution of gold-bearing mineralization, which is a bit like the problematic of the project, the important archive of core samples, and the well-constrained geology. So this is the area. As you can see, from west to east, it is divided in 6 different blocks. So we have Ogmito, Cinderella, Lake Gimbal, Astoria, East Bay, and Buzan. From Ogmito to Astoria, we have the endowed sectors, as you can see with the multiple ore shoots and the important high gold content. However, when we go further east towards East Bay and Buzan, the less endowed sectors, we have almost a complete loss of gold mineralization, except this low patch that's a bit hard to find of 5 gram per ton per meter. So the study area is located in the Neo-Archean Abitibi Greenstone Belt, like I said, 12 kilometers along the Cadillac-Larder Lake Deformation Zone. Itself hosts of multiple orogenic gold deposits in the Abitibi. From north to south, we encounter the mafic and submarine volcanic rocks of the Blake River Group, which are in green. We then encounter the sedimentary rocks, mostly Gerwakis and conglomerates of the Temiskaming Group. And here in between, we can find in dark purple the ultramafic and mafic rocks of the Pichet Group that are now altered in carbonate, chlorite, and talc schists. The Pichet Group is also the physical expression of the Cadillac-Larder Lake Deformation Zone. There's also some observations that we can already make on the field between the endowed and less endowed areas. For example, we can see that the thickness of the Pichet Group decreases importantly towards the less endowed areas. And there's also a slight shift in the orientation that goes from east-west to northeast-southwest. Also, we lose the northern part of the Temiskaming Group, where the Pichet Group here is directly in contact with the Blake River Group to the north. The mineralization is usually associated with veins of quartz carbonate tourmaline within the Pichet Group or in the southern contact between the Pichet and the Temiskaming groups. Gold is found as free gold or as visible and invisible gold inclusion, or even in gold and sulfide matrix such as arsenopyrite, pyrite, and pyrrhotite. There's also differences between the veins in both sectors, which are the the veins in the endowed areas have a carbonate phase that's the ferruginous dolomite, whereas the less endowed area is dominated by the calcite. So we sampled veins and associated host rocks within the lower Pichet, which is the main target for gold mineralization. And it's also from where this figure has been made from. We tried to sample following a regular grid in the X and Z axis as much as possible. So we sampled the endowed areas as well as the less endowed areas. But we also sampled areas with no significant gold content within the endowed areas, just as a comparative standpoint. So afterwards, we established a paragenetic sequence to help in more thorough selections of samples that would be associated with hydrothermal gold-related events. From those veins, we analyzed for their isotopic signatures to observe if there is a spatial variations of those signatures across the segment. For veins where we could have minerals in equilibrium, we could calculate the fluid temperature using the stable isotope geothermometer. And we could see if there is a spatial variation with the fluid temperature. Knowing the temperature, we can then calculate the fluid stable isotope composition of oxygen and hydrogen, for example, from those mineral pairs at known temperature, and then establish the source of the fluid. With all that in mind, we can then put the data and try to model the fluid flow condition and try to replicate the data observed on the field with the hydrogeosphere software. So there's two main components of the results that I'm going to present today. First of all, there's a stable isotope geochemistry and the fluid flow modeling. So let's start with geochemistry. First of all, just take a look at this legend here, because it's going to be the same color scheme I'm going to be using throughout this whole presentation. So the less endowed areas have blue colors, and the brighter colors are related to endowed areas. So as we can see from delta 18 of quartz and tourmaline from veins, we can see there's no spatial variation of delta 18 signature between the sectors. If we take the same data but compare it with gold content, where in gray colors, it's veins with less than 1 gram per ton of gold, and in brown colors, it's veins with over 1 gram per ton of gold. We can see still there's no specific delta 18 signature for gold mineralization. If we compare here with the delta D of the tourmaline, we can see there's no spatial variation for between the sectors. However, if we look at the delta 18 of the carbonates, we can see that the less endowed sectors seem to be related to higher delta 18 values, which is probably simply due to the fact that we find different types of carbonates there. So it's calcite. So calcite is related to higher delta 18 values in this area, and ferruginous dolomite to lower values. So if we take the same data and compare it to gold content, there's no specific signature for the delta D of tourmaline, but we see a correlation with the veins over 1 gram per ton of gold with lower delta 18 values related to the ferruginous dolomite. So for the samples that we had that were in equilibrium, with quartz and tourmalines were in equilibrium together, we could calculate the temperature using this figure, this equation. The black dots represent the Val d'Or vein field, just as a comparative standpoint again. So as we can see here, we can see that my values fall into the typical range of temperature of orogenic gold deposits. But we can see that it's not an isothermal system. We can see there's some fluctuations there. What's interesting here is, like Benoit and Christophe just showed, there's a shift in the delta 18 values where my values are way higher. So it was first thought to be maybe related to my samples being directly in a first order fault versus higher order faults for the Val d'Or vein field. So if we plot those temperature values versus the depth of the sample, we can see that there's an important thermal gradient of approximately 35 degrees per 100 meter, which is way higher than the typical geothermal gradient, of course. So this could be associated with a possible mixing zone. So the advection of high temperature fluid with mixing with lower temperature pore fluids towards the surface. So if we plot those values spatially and we interpolate the data, we can see that there's a rise of high temperature fluid in the Agnito-Cinderella sector, as well as the Astoria sector, which are both high gold content zones. So there's a broad overlap there. However, this interpolation is we have to tread carefully with it because there's not a lot of data to begin with, especially towards the east or towards Lac Gamble. Now, if we take a look, once we know the temperature of formation of each analyzed sample, it's possible to calculate the isotopic signature of the water that crystallized those minerals. And knowing this isotopic signature will help discriminate the source of the fluid and the processes that affected it. So here, it's consistent with the data of temperature versus depth. So we see that there seems to be a mixing of a metamorphic source of high delta 18, low delta D values with an upper crystal source of low delta 18 values. That's most likely Archean seawater trapped in the rock's porosity. However, fluid mixing isn't the only phenomenon that could explain the delta D values, the high delta D values. Like Benoit and Christophe just said, it's most likely due to multiple events of boiling condensations that would enrich the fluid in heavy delta D values. So if we plot those data in the Shepherd diagram for water, we can see that most of the data, some of the data plot directly into the metamorphic box. However, most of the data plot above it, and it's the same thing in the Val d'Or vein field. And like I said, it's possibly simply due to boiling condensation cycles due to the fault valve system. So for the fluid flow modeling part, we made a simple model divided into multiple lithological units based on the Archean units of the geological map right here. The small rectangle inside it is the model. And this is the model, but this is the base model. The hydraulic properties were given to each unit based on the representative values for dominant rock types. For example, for the Timiskaming and the Pontiac group, we gave Pewaukee values. For the Blake River, we gave Intisite values. And for the Piche group, we gave komatiitic schists values. So afterwards, we needed to test out multiple scenarios to find the best boundary conditions that would fit our data the most, as well as a fluid flow direction, using an infiltrating fluid of a composition of 10 per mil, which is our typical metamorphic source, and a pore fluid of 1 per mil, which is our upper crystal source based on previous observations. So from those, we've seen that the best scenario is A, where we could see a change in the isotopic composition of the fluid with the thinning of the Piche group, as well as its change in orientation and the loss of the absence of the northern Timiskaming basin. And the other scenario only showed an homogeneous and constant composition of the fluid through time, which is not what we observed on the field. We've also chosen a vertical flow, but an upward and west-leaning fluid flow direction is not rejected hypothesis. So this is a view into the Piche group. Now that we have the boundary conditions and the fluid flow direction, our goal is to test multiple scenarios that could replicate those field observations. So those are the field observations. And the best scenario was the presence of high conductivity corridors in the Agnito-Cinderella and the Astoria sectors, So we gave an order of magnitude higher conductivity in those sectors, but the same porosity and same reaction rate. We also tried to replicate the thermal gradient observed on the field by giving decreasing fractionation factors for the temperature towards the surface. So if we take a look at the model throughout time, we can see here after 1,000 years, what's interesting here is we can see an important shift where the Pichet group is way thinner, and where when it changes its orientation, and when we also lose the northern Temiskaming basin. So this is after 1,000 years, this is after 5,000 years, and this is after 10,000 years. So afterwards, if we go further through time, the model doesn't fit as well the data as we observed. So to form the isotopic zonation, we need a short-lived hydrothermal system, which is consistent with the literature as well. So if we compare, it's pretty accurate. So in conclusion, the stable isotopes, we can say that the veins come from the same orogenic system across property, that there is no specific isotopic signature for gold mineralization, that there was an important thermal gradient within the Pichet group. That's probably a mixing zone. The mixing zone would probably be mixing of a deep-seated metamorphic fluid of high delta 18, low delta D, and high temperature, with an upper crystal fluid of low delta 18, a delta D around 0, and low temperatures. Upwelling of high temperature and high delta 18 metamorphic fluid also broadly overlaps with high gold content zones. For the fluid flow modeling conclusions, we can say that there probably was some high conductivity corridors in the Agnito, Cinderella, and Astoria sectors, allowing an important rise of gold-bearing metamorphic fluid. And the changes, we can say that the changes in orientation and thickness of the Pichet group, as well as the absence of the northern Temiskaming basin, could influence the hydrodynamics and therefore the gold endowment. What's next for my project? I still need to interpret a bit of the data and finish writing my thesis, hopefully in initial deposits around January. So thank you everyone for listening.
Do we have any questions? When you go into the boost, it's never been clear to me, because we actually did quite a bit of work in a past life in on the project. Is there any Pichet preserved in the Bouzon area, or does it go directly from Temiskaming into Blake River rocks?
There is some Pichet, but it's way, way, way thinner. So
like a meter or so thick or something?
I think there is like some areas that's like 30 meters, and some areas it's like, yeah, that's like 10 meters.
Okay, but is it, do you have the green carbonate alteration, or is
oh no, it's not the same type of alteration.
Chlorite?
It's carbonate, but without the full site. So it's mostly calcite, talc, and some carbonate alteration that could look like it's related to gold, but it's really not.
Okay, excellent, great. Thank you very much. Great presentation.